Here we are in section 2.2, which is called Properties of Matrix Operations. In the last section, we introduced the idea of some important matrix operations. We talked about matrix addition, matrix scalar multiplication, and the really important one, matrix multiplication. And here in this section, we look a little bit at the nitty-gritty of what's legal and what's not legal and what works out in a way that we think it should. We're just going to look at some examples of really the properties of those operations. We're going to do a little comparing and contrasting between real numbers and matrices. We want to see which properties from real numbers will still work with matrices, and we want to especially highlight the properties in real numbers that work that don't work with matrices. So first we're going to look at real numbers. Say that a equals 3 and b equals 2. Then a times b is going to be 3 times 2, and that equals 6. And b times a, right here, that will be 2 times 3. And that's the same thing. That's just 6, both of them. Either way, either order that you put them in, the product is going to be 6. And there's a name for this law. And the name for this law, you'll probably remember it once I start writing it, or maybe you already remember it, is the name commutativity. So real numbers are commutative, multiplicatively. If you multiply them in either order, you're going to get the same result. So now let's go to what we're learning now in this course, matrices, and talk about the idea of commutativity here. And here we've got two matrices. A is this 2 by 2 matrix, and B is this 2 by 2 matrix. With matrices, we have to ask, can we even multiply these two matrices? You know, is the product AB a real thing? Is that going to work out? And luckily, because of their dimensions both being 2 by 2, we can multiply them either way. We can look at A times B, and we can look at B times A. So A is this nice 2 by 2 matrix, and B is also a 2 by 2 matrix because this number of columns equals this number of rows. We know the multiplication is possible to find AB, and the result will be a 2 by 2 matrix. Anyway, around these two matrices, the product is possible, and the result is going to be the same size. It's going to be a 2 by 2 matrix. So let's start with taking the matrix A times the matrix B. And to do this, we're going to take this row and combine it with this column in that special way. We'll take 1 times 2, which is 2, plus 5 times 1. So right in that first entry, we're going to get 7. And then we'll take the same row. Now with this column, 1 times 3 is 3, 5 times 4 is 20. So we should get 23 right here. We're going to just plug it along. We're on the second row. So 2, and we're going to deal with this first column here. So 2 times 2 is 4, plus 3 times 1, that's going to be 7. And last entry, 2 times 3, or 2 and 3 and 3 and 4. So 2 times 3 is 6, 3 times 4 is 12, so that's going to give us 18. Now we'll go the opposite way. We're going to find the product B times A. So we have to do a little bit of mental gymnastics here when we think about taking this row combined with this first column. And that's 2 times 1 is 2, 3 times 2 is 6. So the first entry is 8. Already we see that these are not going to be equal matrices. Let's go ahead and finish it off though. 2 and 3 with 5 and 3, that's 10 plus 9 is 19. And now this row here with this column, that's 1 plus 8, which is 9. And last one, 1 and 4, 5 and 3, that's 5 plus 12, that's 17. So here we see that AB is not equal to BA in this example, which indicates that multiplicative commutativity does not hold in general, does not hold in general for matrices. This law is so ingrained in us because, all our lives we've been dealing with real numbers, and it always works that you can multiply either direction. We're really going to have to watch ourselves this semester that we don't fall into the trap of thinking that AB equals BA for any matrix. Sometimes it does work out that they're equal, but in general, we can't assume this is true. So we're really going to have to, like I say, watch ourselves and remember this fact that we can't assume this is true. Can you think of a matrix C where it would be true that AC equals CA? So can you think of a matrix C such that in this case, this particular A, AC will equal CA, that there is that commutative relationship? I'm going to leave this as a question for the quiz and just tell you that there is one, and it's kind of a trivial one. We talked about it in the last section. There's a matrix that does commute with A and actually commutes with any matrix that it's allowed to multiply with. So we'll leave that as a question for the quiz. So for us, for now, this is the important fact we want to keep in our brains, that multiplication is not necessarily commutative with matrices. Okay, we're going to keep going with the comparisons between real numbers and matrices. Let's say that A equals 5 and B equals 7, and we also know this relationship, that AB equals AC. Then could we determine what C is? So can we find C? And we've done this a million times, and it doesn't seem too hard. We would say, okay, so let's see, A is 5, B is 7, A is still 5, and we have this C that we don't know. And in regular old algebra, we would just divide both sides by 5, and then we find out that C equals 7. And this would be the solution. We, in fact, knew from the beginning that B and C were going to be equal numbers. So C equals B. And that's an important realization to make in this problem. If A times a number equals A times some other thing, then these two things must be equal. That's a property of real numbers. Okay, let's talk about matrices in a similar way. So let's let A equal this matrix, and B is going to be this matrix, and C is this matrix. So 3 different matrices. And we're going to take A times B and find out what that product is. So I know it's going to be a 2 by 2 matrix. Let's see, we've got 1 plus 5 times 0 is 0. So that's 1. Then we've got this row and this column that looks like it's going to be all zeros. And this row with this column, that's a 2 and a 0. And then this, this row in this column, which will be 0. And that is A times B, this guy. Now we're going to look at A times C, and if these were real numbers, we would expect this to be a totally different product than this, because you're multiplying A by a different object. It's not the same thing as B, but we'll see what we get. We see that in this first row, first column, we get 0 plus 5 times 1/5 is 1. And then this row and this column will get all zeros. And this row and this column, okay, 2 times 0 is 0, 10 times 1/5 is 2. And then this row and this column, we get all zeros. So this is something new. We see that A can be multiplied by something and get a matrix, and then you multiply A by a totally different matrix and get the same matrix. This doesn't follow the rules of real numbers, where in real numbers there's sort of this canceling ability. Well, if you know that in matrices AB which is this guy, equals AC, which is this guy, you can't say automatically that B and C are equal. So we can say it's true that AB equals AC here, but B does not equal C. So canceling in the way we were able to do it in real numbers, we can't use that with matrices. Okay, we've seen that multiplicative commutativity doesn't work necessarily in matrices, and now we see that you can't cancel in the same way that we used to be able to with real numbers to solve equations. We're going to have to use different methods, and we'll get some good practice with that. So that's two ways that matrices are really different from operations in real numbers as far as multiplication goes. There's one more we're going to talk about. Here's the next question I want us to think about. If A times B equals 0 and we're in real numbers, what do we know about either A or B? This is a fact we use all the time. You saw it a lot in college algebra when you were like factoring quadratic equations, for example. So one thing we know, if two things multiply to 0, in real numbers, we know that one of them has to be equal to 0. So either A equals 0 or B equals 0 or both. You can't have a product that equals 0 without one of these factors actually being 0 in real numbers. So you probably can already tell what I'm going to draw out when we're talking about matrices. If matrices are somehow different than this, then when we have two matrices that multiply to 0, you can probably guess what might happen. So here we have two matrices, A and B, and let's look at their product, A times B. Okay, I'm going to take this row and this column. That's going to be 1 plus -1 is 0. And then this row and this column's all zeros, so I'm going to get 0 there. And this column, okay, this row is a bunch of zeros, so whatever I operate it with is going to turn into a 0. So we've just seen it. We've seen this A times B where neither original factor was 0, but when you multiply them, we got the 0 matrix. So this is something that can happen with matrices, that those factors, those non-zero factors, can multiply to a 0 matrix. So A wasn't 0 and B wasn't 0, but their product ended up being 0. So from these three examples, we'll remember, first of all, A times B does not equal B times A in general. What do I mean by in general? Sometimes just by sheer luck, they actually do equal each other with matrices. AB might equal BA, but it's not guaranteed. There's no way that you know for sure that when you multiply them one way, they're going to be equal by multiplying them the other way. Usually they're not. Second, we saw that AB, if it equals AC, you don't necessarily know that B and C are equal. It doesn't imply that from the statement. And last, we just saw that if A times B equals 0, this does not imply that one of those guys has to be equal to 0. Two matrices can produce the 0 matrix through multiplication without being 0 themselves. At this point, we're tempted to ask ourselves, okay, what the heck does work with matrices then? What are the properties that hold, the properties that we love from real numbers? Which ones do work with matrices? And the answer is most everything else. We see here all the properties of matrix addition and scalar multiplication. These were just like with vectors, and things work out really well here. With properties of matrix multiplication, here we see the associativity or the associative law. That checks out. Here the distributive property works still with matrices, both of these. Here's the multiplicative identity. Multiplicative identity works either direction. And right here, this guy is, it gives us the ability to move this scalar r kind of almost anywhere we want. We can multiply r by a first, or we can take r and multiply it by b first. So that property holds up. So the only thing that we have to be careful of is the one we've already talked about, that in general, there's multiplication of matrices is not commutative. Now that we've got these guys under our belt, there are a few properties of powers of a matrix. We can take a matrix multiplied by itself if it's a square matrix. And we want to talk real quickly about some of those properties that do hold over from real numbers. And then we'll be kind of all done with all this property talk today. Okay, if A is an n by n matrix, so it's a square matrix, and R and S are non-negative integers. Okay, let's think about what a non-negative integer, what does that mean? So like 1, 2, 3, can't take -3, can't take -4. We want just non-negative. So even 0 is okay because that's a non-negative integer. 0, counting all the way up, all those counting numbers. Then we know three things. A to the R times A to the S, remember these guys are matrices here, or it's the same matrix, is equal to A. In real numbers, do you remember this property? It's going to be A to the R plus S. So that holds through with matrices. Another one kind of goes along with this, A to the R and then to the S power. With real numbers, we knew that we could just multiply these powers, and it's the same story with matrices. This will be equal to A to the RS. And the last one is we're going to define A to the 0. Usually in real numbers, this is the number 1. We're going to define it to be the identity matrix. So these are three more properties that we know will work with matrices. And so we have actually a lot of properties that hold through. We started this session talking about the things that don't work out. Commutativity is the big one, that commutativity does not work out with matrices. But in actuality, there's a lot of things that do work with matrices the same way that they were working with real numbers. So we can't complain too much. We just want to remember this guy here. Before we talk about our last really big topic of this section, I want to step aside for a minute and just make a note of, what if you have the product of several matrices, a big long chain of matrices like A, B, C, D, E, F. You're multiplying all of those together. We know how to detect what the size of the product is going to be with two matrices. We talked about that. But with a big long chain, how do we even know if things are going to work out that you could multiply them? And in the end, how do we know what the size of the resulting matrix should be? So let's say we have three matrices that we're multiplying together, A, B, and C. And A is, we'll say it's a 4 by 7 matrix. And B is going to be a 7 by, 20 matrix. So it has 20 columns. And C will be a matrix of size 20 by 37. So these are really different sizes. Can we multiply all of these together? Well, we'll start, can A and B be multiplied together? Yeah, they can, because these two numbers match. The number of columns in A matches the number of rows in B, and that's exactly what we need. And from A and B, we'll get a 4 by 20 matrix, right? So these two will result in a 4 by 20 matrix. Could that then be multiplied by C? Yeah, absolutely, because these guys match up, those 20s, and the result would be a 4 by 37 matrix. And that's what ABC will be. The dimensions of ABC will be that, this many rows and this many columns here. So when you have a big long string of matrices, and you could have 100 of them, we see that as long as things are matching up and you really can do the multiplication, that the size of the resulting matrix, the product of all of them, will be the number of rows in the first matrix by the number of columns in the last matrix. Okay, I'm going to make this guy kind of tiny because that was just a little side note. At this point, we're going to introduce a new idea that will follow us for the rest of the course. And it's a pretty big introduction. Okay, we're going to think of a new way to think of systems of equations. This is how we started the whole course. When we want to solve systems of equations, we've been using these matrices and RREF, which we're still going to use, but we're going to tweak it just a little bit. So here we have a system of equations. Let's see, we've got 3 variables and 3 equations here. And the old way of handling this, which is still good, was we would take the coefficients, we'd put them in this matrix, and then we would take the constant terms and just put them as the last column in that matrix. And we would do reduced row echelon to this matrix, and we would read off the solutions once it was in that form. So that was all good. We're just going to think about a new way of tackling this problem. So now instead of using just one matrix, I'm going to use these three matrices, and I'm going to put some numbers in, and then I want you to think about what else should go in there. If I put 3, 2, -5 in right here, and if I put the 7 over here, what do you think should go in here from what we know about matrix multiplication? You know, here we are going to have this 3 by 3 matrix multiplied by a 3 by 1 vector, and then we're going to get out a 3 by 1 vector. So with a normal matrix multiplication, we would take this and operate it with this column here. We'd take the corresponding terms and multiply them and then add them all together to get this 7. So what should this column here be? Let's see, we would need 3 to get multiplied by x1. We would need 2 to get multiplied by x2. And we would need -5 to get multiplied by x3. And that should do the trick. That should get us the 7 that we need. We'd take this row with this, not times, but with this column, and we would get that 7. Okay, and then does it work for the rest of what's going on? Let's see. Let's think about this. The coefficients of that would be 1, -8, 4. And if we put the 9 here, let's see, this row and this column would give us 1x1 minus 8x2 plus 4x3 equals 9. That looks right. Okay, the last thing to do is that last row. So 2, 6, -7, and a -2 would go over here. Okay, this row with this column 2x1 plus 6x2 minus 7x3 should equal -2. Yep, that's what the last line says. Why are we even doing this? Well, a lot of reasons. We've just spent a few minutes dealing with all these properties of matrix multiplication and of matrix algebra, really, and we're going to use a lot of those properties in dealing with, exploring, and expanding on the ideas of this statement. And we kind of needed those properties to be able to develop this algebra with matrices. But we have it now, and so we're going to really max it out. So this is a new way of writing this system of equations using matrices. So a long time ago, we said that the set of solutions to a homogeneous system of equations is a subspace. It always is a subspace. And we kind of just presented that idea, and we didn't really prove why it is. We just said it is. Well, you're all becoming more sophisticated in mathematics, and you can't just present ideas without justifying them. So we're going to go back, and now that we have the tools that will help us show why this is true, we're going to look at why this would be true. The set of solutions, remember, a homogeneous system is the system of equations where all those constant terms on the other side of the equal sign are 0. They're always subspaces, and for the first time we can kind of show why that's true. To show something's a subspace, we've got to show that it's closed under vector addition and closed under scalar multiplication. Let's go back up here for a minute and talk about one more type of notation. If I have this matrix here, this random matrix of the coefficients, I'm going to call that, or I can call that, A. That's this matrix. And this matrix that's full of these variables, x, a good name for that would be a capital X. And then this matrix that's just all of the constant terms on the other side of the equal sign, we can call that whatever we want. We'll call it matrix B. So now we have a way of saying all of this in matrix language would just be A times X equals B. So that's a really concise way of describing this system of equation. It's this matrix A times this vector X, and that equals B. Okay, with a homogeneous system, we would have our matrix A of all those coefficients times the vector x, and we would have that equal 0, right? Because it would be the 0 vector, because all of these constant terms in a homogeneous system will be 0. So say we have two solutions to this system here, and we can call one of them x1 and one of them x2. So say that x1 and the vector x2 are solutions to the homogeneous system. So this is a system that has multiple solutions. We're trying to show that all of those solutions will be a subspace. Then wouldn't it be true that A times x1 equals the 0 vector, and A times x2 equals the 0 vector? And now, knowing what we know about properties of matrix algebra, matrix addition, matrix multiplication, we could say that A x1 plus A x2 would also equal 0. And that leads to, using the distributive property that we know we have with matrices, we could say that this is true. Okay, if the matrix of coefficients times some other vector here, I should write, these are all vectors, of course. But this is a new vector. It's a new vector, but it also happens to be a solution to the system, because A times this thing equals 0. So this shows that the sum of those solutions is also a solution. That this sum here follows the rule to be a solution to this homogeneous system, and that implies that we're closed under vector addition. Okay? We've proven that much. Now let's take a look at scalar multiplication. Okay, if we know that how about we try A times this equals 0, and we do know that because x1 is a solution. Then let's look at the scalar multiple of this solution. Is then, call it C for some scalar, x1 also a solution? Well, from this statement right here, we know that just how scalars work. We could say C times the left side, which is a vector, will equal C times the right side. C times the right side is just the 0 vector all over again. And right here, because of what we talked about today with properties of scalars and matrix multiplication, we can move this C right in here. And we could say that this is true. Well, if that's true, then definitely C times the vector x1 is the 0 vector, which makes this a solution. And so we've proven that a scalar multiple of a solution is a solution as well. That means that this set is closed under scalar multiplication. So this right here shows that Cx1 is, you know what, let's write this in red since it's a conclusion. C times the vector x1 is also a solution. These are things that we couldn't have said before. We had all these properties of matrix algebra, but now we do. And so because we've shown that this set is closed under vector addition and closed under scalar multiplication. This is what leads us to say that solutions to a homogeneous system of equations is a subspace. So that set of solutions is a subspace. Okay, so again, this is a fact that we've been using without proof for a while, but now we know that if we have two solutions to this homogeneous system that add them up together, and that's still a solution, that's closure under addition, and you can look at a scalar multiple of a solution and it also will be a solution. So that's closure under scalar multiplication. It's a subspace. So this is sort of informally written proof of that set being a subspace. Let's look for a minute at non-homogeneous systems. So let's take a solution to a non-homogeneous system. Let's take two solutions. And remember, a non-homogeneous system is just one where your constant terms are not all zero. There's some constant numbers like 4, -3, 2 on that other side of the equal sign. Okay, if they're both solutions, then this statement is true. ax1 equals b and ax2 equals b. Remember, we're thinking of all of these as matrices here. So then we want to think, is this also a subspace, this set of solutions to a non-homogeneous system? We've given so much attention to homogeneous systems, but could the set of solutions to a non-homogeneous system also be a subspace? Let's take these and add them together and see what these two equations throw out. If I just use some properties of matrix addition, I'm going to add these two guys together, and they should equal, what should they equal? Let's see, they should equal b plus b, or 2b. Using the distributive property sort of backwards, we could say that this is true. All of a sudden, this is a problem. The sum of those two solutions actually is not a solution. It yields something else. Remember, these are the coefficients in the original system of equations. This matrix A, that's what it's holding. And when I tried to take the sum of the two solutions that I know and work them with this matrix of coefficients, I did not get the what I should have gotten. What I should have gotten was b. If I'd gotten a b over here, then I would know that this guy is another solution, but I didn't. I got 2b. So this implies that the sum of these two solutions are not solutions themselves, or is not a solution itself. So at this point, we have to say, whoa, x1 plus x2, this is just another vector. It's the sum of those two vectors, is not a solution to the system. So the set of solutions is not closed under vector addition. And so importantly, that set is not a subspace. It would also fail with scalar multiplication as well. But once we know that it fails vector addition, we know it's not a subspace. So in general, we can say that the set of solutions to a non-homogeneous system is not a subspace. So that whole group, that whole gaggle of solutions to a homogeneous system, they follow the rules really well to form a subspace. But these non-homogeneous systems, their solutions, they don't behave well enough to stay closed under vector addition or scalar multiplication, and so they will not be a subspace. But there is one idea we need to talk about, and that is with every non-homogeneous system, there is a corresponding homogeneous system. And I'll put a dot, dot, dot. What do I mean by that? Well, with every non-homogeneous system, say that you just knocked out all the constant terms and made them zero. That is a corresponding homogeneous system. And what we're going to see in our last example is that understanding things about the homogeneous system helps us understand better the non-homogeneous system that corresponds to it. So let's look at an example and try to figure out what the heck I'm saying. So here we have a system of equations, and you think in your head, is this a homogeneous system or a non-homogeneous system? Because we have these non-zero constants over here, this is definitely a non-homogeneous system. So non-homogeneous. And this is a system that will have an infinite number of solutions, and they all look like this. These are the solutions to this system, to this non-homogeneous system. Think for a minute what the corresponding homogeneous system should look like in your head. Well, it looks exactly like this one, except I'm going to take off these constant terms and I'm going to replace them with zeros. This is the corresponding homogeneous system. So here is that corresponding homogeneous system, and it too has a solution. It has many solutions, and so we can write, I didn't go through all the work here, but we've done this plenty of times. The general solution to this guy looks like this. R, negative 2R, R. And you can already start to see how the solution here looks a lot like the solution here. There's a few extra things here. And what does that mean? Let's start by trying to visualize this guy. This is R times 1, negative 2, 1. So if we had these three axes, and we've got x1 right here, and x2 here, and x3 here, this is saying take any scalar multiple of the vector 1, negative 2, 1. So 1, negative 2, 1, let's see, that's going to be 1, then like negative 2, and then 1 up here. So there's some vector 1, negative 2, and then up 1 that looks like this. And all of the scalar multiples of that vector are a solution to this system. That's what this means. All the scalar multiples of that vector are a solution to this system. And so that forms a line. So that's going to look something like, goes off infinitely this way and infinitely that way. It should be a straight line. Let's try that again. Go kind of slow here. It's going to be this straight line through the origin. That didn't go very well. Okay, let's move this line to make it fit the vector. Okay, this is a little better. These are all the solutions to the homogeneous system here on this line. Okay, now let's think about what this line should look like. So let's pull out an R. It'll equal R times 1, negative 2, 1. But then there's a few other leftover things. There's a negative 1, a 3, and then 0. So this vector here is going to be, let's see, negative 1 on the x1 axis, about right there, and then 3 on the x2, 1, 2, 3, and then 0 up. So that negative 1, 3, 0 looks something like that. We are going to, so when we're taking this whole set, which is essentially this red line, plus this vector, it's going to shift this line over in that direction. And we get this new set of solutions for all the non-homogeneous for the non-homogeneous system. So you can see how the solutions here are related to the solutions here. All of these guys here, any point on this line will be a solution to the non-homogeneous system. It doesn't go through the point 0, 0, 0. It's not a subspace, it's just a subset. And then these here are all the solutions to the corresponding homogeneous system, which does go through 0, 0, 0, and it is a subspace. It follows all the rules, but they're definitely related, and we can see that here. Okay, let's talk about the big ideas we saw today. And today was a pretty heavy theory day. We talked about so many theoretical things and abstract things today. Probably the three biggest ideas were, we spent quite a bit of time talking about properties of matrix operations. We know that matrix algebra is not, we cannot use the commutative law multiplicatively. That's a big one. And we looked at a new way of writing systems of equations using the algebra of matrices, that AX equals B, where things were all matrices. And now just in these last few discussions, examples, we looked at the link between a homogeneous system or a non-homogeneous system and its corresponding homogeneous system, and what one can tell us about the other.